Can you figure out the big O of this function? Hey, I'm Tara, I'm a senior software engineer, and I used to teach computer science at Carnegie Mellon. I'll give you multiple choice again for this one. O of n squared, O of n log n, or O of n. If you said O of n log n, you are correct, and I would love to walk you through it. So, okay, let's start off with n equal to 8. So we have a nice for loop here, and we go from 1 all the way up to 8. And so we start off with I equal to 1. Okay, so we set j equal to I, and we say while j is less than n, we increment it by I. So in this first round, we're going to go all the way till j equals 8. So we're going to go basically from 1 to 8. And each time we're going to add I to it, and I is just 1. So we're going to add 1. So basically we're going to do 8 units of work in this first round. I'll keep track of that down here. So total work is equal to 8. Okay, cool. All right, next round, I is going to equal 2. So now j is going to be equal to 2. So we're going to have j go from 2 to 8. But how many times does this run? Because we're not adding 1 anymore. We're actually adding 2. And so it's kind of like, how many times does 2 go into 8? And the answer for that is 4. So this will run 4 times. And so we will do 4 units of work. All right, let's keep going till we see a pattern. And so now I is equal to 3. So we'll set j equal to I. So now j is going to go from 3 to 8. But this time we're actually adding 3. So how many times does 3 go into 8 evenly? It's 2 times and some change. And so we're going to do 2 units of work here, right? Because first it'll be 3, and then it will be 6. But then it will go to 9, and we'll be done. So now let us set I equal to 4. So now j is equal to 4, so j is going to go from 4 to 8. But now we're adding 4. Do you see a pattern here? Basically, this inner loop is running n divided by I times. It's like, how many times does I go into n? And so 4 goes into 8 2 times. All right, let's just finish this out. So I is equal to 5. Well, how many times does 5 go evenly into 8? 8 divided by 5 is 1.75. We round that down, and so we're doing 1 unit of work. Okay, what about when I is 6? Well, 8 divided by 6 is 1.5. That will also round down. And then finally, actually not finally, we got 7 here. Okay, so then 8 divided by 7 is 1.25. That also rounds down to 1. And finally, we got 8. Because this loop is inclusive of 8. We add 8, so this loop only runs 1 time as well. 8 divided by 8 is equal to 1. So this is interesting. We got 20 units of work here. So here's our function from before. Same thing we just talked through. And we're running a summation here to figure out this total amount of work, and we're going to try to generalize it. So we start I off at 1, but then how many terms are in this final series that we've created? Well, it's actually n terms, and we can see here that this for loop runs from 1 to n plus 1, so the for loop is running n times. And then what happens on each loop? How much work happens on each loop? We actually talked about this already, but we said that it's n divided by I. So I can actually factor out n, so that's just the same thing that we had before. So now the question is, like, what is this thing? And this is very mathy, but this actually, you might recognize this. So this is actually the harmonic series, and the harmonic series looks something like this. It's 1 plus 1/2 plus 1/3 plus 1/4. And we know that this thing, as n grows large, it grows like log n. And so this whole thing is actually O of n log n. Okay, but like, how can we prove that the harmonic series grows like log n asymptotically, so for large values of n? Well, first I want to show the lower bound of this function, and then we'll show the upper bound of this function, and we'll see what it's bounded by. So let's start with the lower bound. So I've drawn out the harmonic series here to some degree. We have 1 plus 1/2 plus 1/3, so on and so forth. So I'm actually going to make groups here, and the groups are going to be sized in powers of 2. And so 1 is kind of a special case here, but let's just make 1 its own group. I'm going to also put 1/2 in its own group. So now I need a group of size 2, so I'm going to grab this 1/3 and this 1/4. And now I need a group of size 4, and so I need this 1/5 up to 1/8. And then my next group would start with 1/9, and it would end with 1/16 because it would be of size 8. And so on and so forth until we get up to n. So how many groups are there? Well, for our example where n equals 8, we see that we have 4 groups. So it's like, how many times can we divide 8 by 2 until we get down to 1? Looks something like this. We have log base 2n groups. Now here's the really cool thing. It's like, how much is each group contributing to in the smallest case? Like, what's the least amount each of these groups is contributing to our total sum? So first we have 1 over here, and we're contributing a minimum of 1 right now. But next we have 1/2. So it's like, okay, well, we're contributing a minimum of 1/2 in each of these groups. But let's look at this next one. So we have 1/3 and we have 1/4. Well, actually, if you were to take the smallest term in this group, which is 1/4, and you were to just multiply it by the total number of terms in this group, which is 2, we would get 2 times 1/4. And so if all of the terms in this group were the smallest term, which is 1/4, then this thing at a minimum would be 1/2. But really 1/3 is bigger than 1/4. So we know that it's greater than 1/2. This one's actually just equal to 1/2. Okay, let's move on to the next group. So if I were to take the smallest term in the next group, which is 1/8, and I were to say, okay, well, now we just have a bunch of 1/8 here. So we have 4 1/8. Well, that would actually also be 1/2. But all of these terms are bigger than 1/8. So we know that we have greater than 1/2 in this group. And that would actually be true for the next groups too. If we look at the next group that has 8 terms, if we did have a next group for a bigger n, for example, then it would be 1/16 times 8. 8 over 16 is also 1/2. So we can say that our harmonic series is going to be greater than or equal to, and then it's going to be 1/2 times log base 2 of n. So that's our lower bound. Okay, so then what is the upper bound? Can we prove the harmonic series is always below a certain value? Yeah, we're going to do it in the same way we showed the lower bound. So here I have my groups again. I got 1, and then I have 1/2, then I have 1/3 and 1/4, then I have 1/5, 1/6, 1/7, and 1/8, and still we're grouping in powers of 2 here. And so that means that we have log base 2 of n groups. Okay, so then what is the maximum value that each of these groups can contribute? Well, we're kind of going to do the opposite that we did last time. This time we're going to look at the largest term. We're like, okay, what's that at a maximum? So when we have 1/3 and 1/4, well, the biggest term is 1/3, and there are 2 terms. And so if we had a bunch of 1/3s here, we would be contributing like 2 over 3. And then in this next group, the biggest term is actually 1 over 5, and we have 4 terms here. And so we are contributing 4 over 5. And even if we think about the next group would go from 1/9 to 1/16, but 1/9 would be the biggest term. So this would be like 1 over 9 to 1/16. And we'd have like 8 terms here. And so the most that this can contribute is 8 over 9. For any group K, if we had K terms in a group, like the biggest term that we have is 1 over K, and kind of like 1 over K plus 1, because if this group has 8 things in it, well, our biggest term is like 1 over 9. And that's never going to be bigger than 1. So at most, we're contributing 1 in any of these groups. The first one contributes 1. And these sort of all start to move towards 1 as the groups get bigger and bigger, but they're never going to be bigger than 1. Our upper bound is 1, because we have this little 1 here, plus, and then whatever all of these guys are bounded by 1. So it's like log n of these that are bounded by 1. So this is actually going to be bounded by the number of groups that we have times 1, but anything multiplied by 1 is just itself. So this is what our upper bound is. And because we're bounded by, our lower bound is log base 2 of n, and our upper log is log base 2 of n, this whole thing behaves like log of n. Thank you for following along, and we'll do some more fun math problems soon.